Hi, let's rock and roll. We'll start. My name is Rafal Szarecki. I will have a second. My second talk today is about strategies used by hardware vendors to buffer the packets inside the router, not switches, routers. So the first question will be, why shall I care how the buffering or queuing inside the stuff is happening? And the reason is because it has implication on the router behavior, on what you observe outside of the box, what traffic is treated how, what is the... And to be frank, this behavior is quite unintuitive. It's not what you can tell on the first look. And it's better to know how the particular router behaves, because then you know if the behavior is expected or not, and how to live with this artificial intelligence of the router. Bottom line, from operation perspective, this allows you to avoid the troubleshooting for non-existing problem. So everything starts from some observed phenomena on the network that SLM monitoring alarms that something is going wrong, or either packet loss or traffic loss, or too high jitter latency. And well, not that rarely, it's a customer call and complaints. And then normal network troubleshooting happens, so we are looking for where the problem is, which node introduced the challenge. And if we are lucky, we find it. It may need go node by node. It may require some help from expert system or whatever. Generally, that's out of scope of my talk, because that's a network level. And we are going inside under the hood of the router. When we nail down the guilty node, the guilty router, what's going there? And the behavior of the router could be quite unintuitive, right? We may observe the situation when we receive the traffic on non-congested port, we send them out from the same traffic, the same flow, from even less congested port, and we still see the packet loss. What the teeth, right? I have wire speed router, and I'm losing my traffic, even my ports are not congested. The other exercise is, yes, we have two flows going out from the common port. The port is congested, so there should be a delay. But some flows are bigger delay than other. Why? It's a bug, or it's expected behavior. Some disclaimer. I'm not going to talk about the QoS. Queuing is not the same as QoS, right? Queuing is just to manage the burst of traffic which cannot be handled just right on time, so I buffer it, delay it, and serve a bit later. QoS is more about saying, okay, this is better traffic, worse traffic, so we'll send one traffic in front of another. We change the order of the packets. Queuing is important part of the QoS, but it's not. Well, the QoS is not enough to say this. The queuing is not a QoS. And as I promised, we are going under the hood of the router, so we have to see anatomy of it, at least to model it to some extent. Not going to very detail, but so we generally on the router we will see it's a three stages thing, right? We have some PFE. I use the PFE as a packet forwarding engine. It's a general term. It could be CPU, NPU, ASIC, yeah, that is, which takes the traffic from the ingress ports, look where this should go, and multiplex them to the fabric port, fabric ingress port. Next stage is a fabric. Switch fabric is something which moves the data from one port to another. And then we have egress stage, egress PFE, which takes the packets from the fabric port and distribute, or actually not distribute, decide to which particular egress interface this traffic should go. From the queuing and congestion perspective, we have three types of the function. Our ingress PFE is actually, from the traffic perspective, is a max. We take the traffic from multiple ingresses and we max it to the single egress toward the fabric. And of course, some products or some particular line cards may be oversubscribed, but that's out of the scope of this talk. It's another level of complexity. I want to avoid it. So let's assume this is a line rate router, which means that the sum of the bandwidth on the ingress interfaces is less or equal to the fabric. In practical implementation, it's always less, but for that, at that stage, we can say it's less or equal. And because of that, there is no way to create the congestion. There is no need to buffer, because there is always bandwidth to whatever we get, we do the header processing or whatever is necessary, and we can push it to the fabric. So that's good, no brainer. But the opposite side of the router, when we're going out, is different, is de-mux. We take the traffic from high-speed interface from the fabric, and the particular traffic may need to go out through the single egress interface or only subset of egress interfaces, which has lower bandwidth than the fabric. And in this case, we may go to the congestion situation. The burst on the fabric interface cannot be served immediately. So we need to either drop that or buffer it and smooth the traffic. And losing the packets is not a good thing, especially for the short burst. So that's why we need the queues here, or buffers here. The last we need buffers, so the buffers would be implemented per egress interface. So it's quite simple mechanics, right? We get the traffic in. There is an indicator which says, okay, this packet should leave the interface 1, 2, 3, or whatever. And there is a buffer which holds the packets if they come too fast to be served immediately. This scheme we call output buffer, output queuing system, because the switching part is first, and then we put the packets to the queue. The important thing is that this part of the system is as fast as the input interface, because we want to be able to put traffic into the queue as fast as we receive it. Otherwise, we'll lose it, right? So the middle part of the router is, from the queuing perspective, more challenging one. It's a switch fabric. And this switch fabric is usually N by N device, and the speeds of the input and outputs are equal. Right? So the picture here shows the switch fabric as a crossbar switch. Of course, it could be a closed switch or whatever, Torus or Banyan network, which is a little bit more complex, but at the proper abstraction level, it's just a black box with the equal number of inputs and outputs, and it has a property that at the given moment of time, they can switch the traffic from all inputs to all outputs simultaneously, but if multiple inputs talks to one output, there would be a congestion. And the crossbar switches are bufferless. There is no way to delay the traffic, right? So we have to deal with that somehow. The basic switch, the input of the basic switch at themselves has no knowledge about state of egress, right? Each each ingress and egress are independent. Okay. That's the congestion, and we have to manage it. And there are, in general, in theory, there are three strategies, three ways to buffer or implement the queue for the fabric. We can do output queuing, similar to previous one, to the de-mux. The challenge with that is, for every queue, we have to deliver. We need the switching element has to be overspeeded, right? So our switch fabric crossbar need to have the bandwidth toward the queue per each egress need to be n times higher than the egress, just to not lose the packets before queue. And we cannot do that. It's technically too expensive. So let's say the switch is 1 terabit. If this element is 1 terabit, or let's say, well, better 10 terabit, this means that internally it has to be like 100 terabits, because it has 100 input and 100 outputs. One chip. We cannot do that. So not going deeper for that one, because it's impractical. Nobody is doing that. The other two are input queuing and virtual output queuing, and I will deep dive a little bit more to these two. The input queue requires some fabric scheduler and the queues before fabric element, before switching element. So in this model, there is as I said, fabric scheduler. So there is a control plane or control flow from the egress port to ingress port, which allows the ingress port to talk to the egress. Because we have only one queue, we will need some overspeed as well. And this overspeed in theory is double. So we need the switching fabric has to be twice faster than actual the input and output interfaces. So how it works? The color coding here is that it's like we have a blue interface, red interface, and green interface, and the packets which supposed to leave these interfaces are also color coded the same way. And we have some packets in the ingress queues. So what happens? We have a request. So each queue, from the head of the queue, there is a request for the transmission to the egress port for given packet. So as you see, we have the request for blue, request for green, even two requests for blue, because two queues, two ingresses has the packet on front, which is supposed to go to some same destination. That's an example of congestion. But only one ingress gets the grant. Simple. But not very efficient. This packet, the red packet, in the port number 1, it starts from 0. So this packet, theoretically, it could be sent over the fabric, right? The output port is empty. It's ready to get the traffic. But because the packet is not the first in the queue, there was no even request for it. So traffic goes. Then we have another grant message, another traffic. And finally, sooner or later, but this red packet will be served as well. But it's clear now, it should be clear now, that fabric is not utilized 100%. There are periods of times when some connection in fabric could be made, but packet cannot be pushed to the fabric because it's not on the head of the queue. So now we have VoQ. And this is like extension of the input queuing. So VoQ, virtual output queuing, is actually input queuing, where we have the queue per egress interface, color-coded. So it's virtually output because in fact it's on input. And we have a very similar flow control. So we have a request, and then, of course, for the packets which are on the head of the queue, we have a request going forward in the fabric. And you can see that we have the blue request from all interfaces and green request from the interfaces which has the green packet on the head of the green queue, and the same for the red one. Of course, the ports, the egress part, or arbiter of the fabric, which is effectively the same thing, gives the grants. And they give the grants only to one queue at a time. In this case, our red traffic, which was blocked previously, now goes through. So going back to the router, we say it's a 3 stages. We have ingress, and there is no need for queuing for that max function. We have the fabric, and we discussed 2 strategies for queuing for the fabric part. It's input queuing or VoQ. And we have the egress de-mux, and we also discussed that output queuing is the strategy used here. But when we put everything together, guess what? We have 2 options. So option number 1 is a buffer twice. And this class of the system are called combined input-output queuing, which means that we have a queue before fabric and on the output interface. It's 2 buffers, 2 memories, 2 flow controls, 2 schedulers. And this kind of system nowadays are built as a VoQ, fabric VoQ, followed by output interface, output queuing system. These are easier to build. Divide and conquer, right? I have 2 different problems, and I solve them independently. It allows me to higher scale, because the number of the queue are, in the first stage, is our function of number of the fabric ports, and other stage is number of the output interface on a single chip, which is the egress chip, right? So it's, however, I need memory on both parts. I need DRAM I need DRAM to push the traffic to DRAM before fabric, take it from the DRAM, send over the fabric, push them back to the DRAM on egress, take them back to the chip and send out of the interface. This means more memory in space, which is not a big deal. Space memory is not the problem, but I need a memory bandwidth, right? The speed of the memory, how many megabits per second or gigabits per second I can push to the memory for the really fast router today is a challenge. The other option is buffer ones, and this is a moment when we come to the overload this VoQ name. It's a VoQ system end to end. And we have buffer only before fabric. And we take the packet from the memory, from the buffer, only if there is whole path down to the egress interface clean, and we can immediately send. This means that every PFE on ingress has to have as many queue, as many interfaces in the system, regardless of number of slots. So if we have and we are talking potentially about logical interfaces, right? So if the system has 10,000 interfaces, I need 10,000 buffers on every single chip. Plus, and remember, I'm not talking about QS, so times number of queues or classes. That's a scaling challenge, right? To design something like that and schedule across this number of queues, 10,000 is not a big number, but it easily go to the numbers which is 100,000, 300,000 to build some 1 rack system, maybe 2 rack system. So that's a challenge with that. But the benefits I need less memory, space-wise, and also I need to write to memory and read from memory only once, which means that lower bandwidth is needed. Overall, because I'm accessing a memory only once, DRAM memory only once, I have also lower latency across the box. And the latency is nothing about the buffering. It's just because even the non-loaded box with a very little traffic, because of the architecture, packet has to go to the memory and back. Even it's just write and read. That's how it is. And it introduces delay. So VoQ systems are usually has lower residency time and lower power requirements. Why? Because less parts. So how things works with buffer twice approach from the latency perspective. And now I'm talking about the buffering latency, so how much the traffic could be delayed during the congestion. We have two potential congestion points, each of them managed separately. So worst case scenario is when we have the congestion at both points at the same time, and it's possible. We'll see this in an example very soon. Then we have the delay introduced by the VoQ buffer before fabric, and another delay introduced by the output buffer on the egress interface. So it's like maximum latency is sum of these two. This also means or impacts the potential jitter, right? Because if I have a congestion period and then I have non-congested period, the latency difference is a sum of these two. Also, interesting things happens when we talk when we look at the bandwidth fairness or bandwidth allocation for the multiple flows. It's a distributed system, so yeah, we have the flow. Very often we have the traffic which comes to the ingress traffic which comes to the router on different or multiple ingress PFEs on different line cards even, right? So the question is how the fabric scheduler decide which card will be served when and what is the scheduling, what is this scheduling schema. In most cases, it's the arbiter is not aware about amount of incoming traffic. It's only aware that the traffic is there or not. So it's a fair share algorithm. Sometimes weighted if we have different speeds of the ASICs, but for the simplicity of the further examples, everything is very symmetrical, speeds are the same. That's a buffer twice. Okay, so what is end-to-end VoQ system? Buffer once. Well, we treat the second and third stage of the router, so the fabric and egress de-mux as a single switching element, virtually, which has n inputs, m outputs, and the total inputs bandwidth is equal to total output bandwidth. However, because of the different numbers of the ports port speeds are different. The input ports are faster than output. And still, we have two potential congestion points. We can congest the fabric interface, we can congest the output interface. But the scheduler is looking at both places and gives the grant only if there is no congestion on any of them. And because the output interface has lower speed, this congestion usually happens first. Right. What is the impact on latency? Because we have only one buffer, the number of bytes we can buffer is limited. So that's an upper boundary of the latency regardless where the congestion happens. Both places, one place, doesn't matter. With the bandwidth, it's even more complex. Because yes, the fair share approach is used here as well. However, it's a fair share per egress port, not per fabric port, which may lead to the situation when the fabric port is underutilized because we give the shares only for the output interface. We have these two approaches, these two architectures. So now the question is, okay, for what these architectures are good, bad, how to position one against other. And actually, I show three options. CIOQ system with input queuing, not really modern design, but there in the past there was the systems like that. I know Cisco. Probably there were others like that as well, but I just don't know, so don't want to mislead you. CIOQ system with a VoQ fabric and output queuing, and this is majority of system on the market. This is Juniper MX, this is Cisco ASR, this is CRS, this is ALU. All of them are that kind of architecture. And finally, the end-to-end VoQ systems, which is Juniper PTX, as far as I know, NCS 600, no, NCS 6000 is like that. And as I said, end-to-end VoQ system tends to have lower latency, residency time. Behaves very well with the high load, but CIOQ system as well, if there is a VoQ fabric. However, the CIOQ system scales much better when it comes to number of interfaces because of this two stages approach, right? So we not need to have all queues available of all interface queues available on every single PFE. That's why this is a good platform for the application like BNG or maybe very dense VPN PE. So I start this session with the statement that it could be unintuitive behavior, and depending on the queuing strategy, this behavior will be different. So I will give you two examples, and we will walk through it to see why it is. So first, if I say unintuitive, so what is intuitive? Let's look at the bandwidth. That's a like educational example, so the numbers are corner cases, let's say. We offer 700 gig load, which is supposed to go to the single 100 gig interfaces, and this is flows from F1 to F5 of different value each of them. And we have flow F6, very low, which goes out of the 100 gig interface, which is different than that one. So what do we expect intuitively? Okay, flow number 6 should go through, right? Why to lose it? It's wire speed, router. At the end of the day, interface is not congested, no problem. And flows 1 to 5, okay, I load 600 gig, I can get only 100 gigs, so I lose 6. 6 out of 7 is 86% loss expected. Is it intuitive? I think it is. But reality is that router X, that's to not be a vendor specific or platform specific. Actually, the results are different. The losses for the flow of F1 to F5 vary from 82 to 88%. And even more interestingly, more surprisingly, the flow F6 has 50% loss. Why? What the heck? And then let's replace the router X by router Y. Different router, different architecture. Same load. And what we see? Oh, F6, there is no losses. And the losses on the F1 to F5 are still different. There is some consistency between these two, but they are different. So why that? Know your hardware. Router X router X is CIOQ system. Router Y is VoQ system. And looking under the hood, this is a PFEs and Fabric, and the Fabric port is 300 gig in this theoretical platform. I never heard about this kind of router, so that's a good example to not say that I'm vendor specific. And we know that on both routers use the fair share Fabric scheduler. So let's see what happens for the router X. It's CIOQ. Flow F1 and FF2 share the same buffer, same queue on the PFE1 before Fabric. And flow 3 and 4 share the common queue on the PFE2 toward shared Fabric. And 5 and 6 are on PFE3. And they share the same queue. So there is a free ingress PFE that want to talk to the PFE4. Fabric scheduler gives 100 gigabit per second to each of the ingress PFE. That's a fair share scheduler, Fabric scheduler. Because my load is different, I end up with different losses. And even here, this is a reason why I have 50% loss for my F5 stream. Even they are leaving non-congested interface, this warranted boundary, this 100 gig, makes 50% more or less loss for that flow because it shares the same queue as F5. Okay, good. So what is the next stage? Traffic is already arrived on the egress PFE, and this is output queuing system, so flow F1 to F5, which is at 295 gigs after losses on the front of the Fabric, enters the queue, and it will be scheduled out at the 100 gig speed. So it's another 65% loss on top of whatever we already lost before Fabric. And this ends up with 82%. Same logic applies for the flows 3 and 4, which are in the same queue on that stage. F6, there is no congestion. So whatever we get, whatever PFE4 get for the flow F6, it's sent it out. So there is no losses at the second stage. But what we lose before, we lose. And the funny thing is, not so funny thing, is that the Fabric queuing system is not exposed in the CLI. So you need to know how to hack. But, or call JTAG or whatever tag they tells you. But yeah, on the PFE3, we can look for the queue staticity for PFE4, which is the destination PFE, and we see, okay, what is enqueued, put it into the queue, and what is transmitted out of the queue, and what is the drop. That's a 50%. That's example from the previous slide. Good. Router Y. We know that this is VoQ system. So what would be the behavior? We start the same logic, right? So flows F1 and F2 shares the same queue on the PFE1. Flows F3 and F4 shares the same queue on the PFE2. However, flow 5 and flow 6 has dedicated queues. Why? Because flow 6 is going to different output interface. So they have different VoQ here before Fabric. And that's where difference starts. Then the Fabric scheduler is considering the egress port bandwidth availability. So it gives a fair share per output interface. Because output interface, the interface 1, is 100 gig, so 32 gig is given to VoQ at PFE1, 2, and 3, the VoQ for that port. And now everything starts to be obvious, right? Because it's 32 gig given, so we have different losses because the offered load is different on each PFE. We have 300 gig here, 200 gig here, so that's why different loss rate. For the flow 6, the output interface is this is only flow, and only PFE3 is talking to egress interface 2. So 100 gig is guaranteed for this queue. And by the way, it's only 10 gig traffic, so no losses. Then when we go to when the packet arrives on the PFE4, it's already at the speed of interfaces, right? Because interface 1 allocates 3 times 32 gig, so the flow for the interface 1 is 100 gig. There is no need to buffering, and there is no buffer at all in the hardware, so packet go out. Same for the interface 2. So there is no any additional losses or additional congestion at the egress interface. And yeah, same story here. It's even more, this is an example of particular product, but the VoQ number actually means what is the egress interface. But that's internal index number, which is not intuitive. But anyway, you can see that Q drain rate for that interface is 32 gig. Because the situation was like before. So what we can do about that? Not much. We can accept the fact of life. It is what it is. To my knowledge, nobody, no vendor allows you to manipulate the fabric scheduler. And yeah, it seems to be simple from my talk, but believe me, there is a timing, there is distances, there is 1,000 of details. There is a paging, there is an inefficiency of the memory access, there is a selfification tax. There is a lot of things you have to take into the account. So it's a rope, and it's better don't hang yourself. So you have to live with it. However, knowing the behavior, you can find the way to mitigate the problem, right? If you think that your flows are served unfairly, you may reshuffle the traffic, so move some flows from one PFE to another PFE. Because if you fairly load the ingress PFE, you get a fair share for each flow. It's not always possible, I know that. But it's better to know. At least you are not doing the troubleshooting, not raise the tickets, not for non-existing problem. You know it is like that. And potentially next time you choose the other platform or other architecture. Okay, we discussed the losses and boundary things. The next is latency. Example is a little bit simpler, right? We have 3 flows, it's 400 gig altogether. We load it, we direct it to the one output interface, which is 100 gig. And the platform is designed, or that's a vendor statement that, yeah, we have 100 milliseconds buffer, or we can accommodate the burst which is equal to the interface speed times 100 milliseconds. Good. So we expect 100 milliseconds. Because it's a permanent congestion, we expect like 100 milliseconds latency. But funny enough, in a router X case, some flows are delayed by 200 milliseconds. Why? Perpetuum mobile, we delay more than we have memory. Not really. We have more memory than we thought we have. The architecture Y has the 100 milliseconds, shows 100 milliseconds. Why? Because with the CIOQ system, you have buffer before fabric and after fabric. And if my statement as a vendor is that I can survive 100 milliseconds burst, I need the proper memory before fabric because this burst could be against the fabric port. And I need this on the output interface because it could be a situation when fabric is not congested, only port is congested, right? So it's more buffer. And that's the reason why we say it. Again, step by step, flows 1 and 2 shares the fabric VoQ buffer on the PFE1. And if flow F3 is alone, and there is a 2PFE which tries to talk to the egress interface, so each of them gets a fair share of 150 gigabits of the fabric port bandwidth. It's 300 gig port. Flows 1 and 2 are dequeued, taken from the queue at the speed of 200 gigabits. Why 200? It's 150 guaranteed, and there is some left over from the other port, so that from the other PFE, that's why it's 200. So because we take the packet from the queue slower than putting into the queue, we will have a delay. The queue will build up and we will see the 100 milliseconds delay. And some losses, of course. Flow F3 is alone flown on the PFE2, and it has these 50 millisecond, 150 gigabit guaranteed. It not needs that much. It's 100 gigabit only. So actually the queue is empty, right? Because we can take faster, we possibly can take faster traffic than they arrive on the queue. However, when the traffic comes to the egress PFE, that's altogether 300 gigabits traffic. And we try to push it down to the single 100 gig interface. So again, there is a queue, so queue builds up, 100 milliseconds delay. And that's how we end up with 200 milliseconds. Of course, in practical implementation, before fabric buffer could be a little bit more shallow, right? Your vendor don't tell you, but it's not 100 milliseconds, it's only 50 milliseconds. But still, logic is the same. You will end up with 150, not 100. Router Y. You know, this is a VoQ system, right? So we buffer only on the front. Flow F1 and F2 shares the same queue on PFE1. F3 is alone on PFE2. There is a 2 ingress PFE that want to tag to the egress port. So Fabric Scheduler gives a guarantee of 50 gig to each ingress PFE. And then, of course, the ingress in both cases, it's overloaded. So we get the 100 milliseconds delay for flow F1 and F2 with a high drop rate. And flow F3 will be delayed as well before Fabric at the PFE2, but with a bit lower loss rate, but that doesn't matter. That's not our focus. And on the egress, when the traffic arrives from all 3 flows to the PFE4, it's already 100 gig. So there is no need to buffering at all. Okay, that's a exercise. And I stay like that for a while. What we observe, this is a bandwidth and this is a loss rate. So what is the router architecture? That's your homework. If you like to take an exercise, the presentation should be online so you can come back to this slide. I'm waiting for answer. I will try to find some kind of interesting the price, or at least send back the legal table who get the answer first. Summary. Better know your router anatomy, because then you know if they behave as expected or it's a problem. The queuing architecture impacts power consumption and system scaling capabilities, and that's maybe not that important in the operational because you already bought the router, so it's there, but just for your information. But the queuing architecture impacts the residency time. How long, best case, packet has to stay at the router? What is your latency? And the last point is, queuing architecture may be a reason for the non-intuitive traffic loss or latency pattern. if you know that this is expected for the given architecture, you avoid filling the case, explaining to the management that something goes wrong, but it's good, but it's expected, not, right? If you know that this is expected, if you know the architecture, you know this is expected behavior, then at least you can try to mitigate the problem if you need, or just leave it at, but you avoid the hassle with the dealing with the tech support, explaining, sends the thousands of logs, waits a week, escalate, have the calls and questions from management why and what's going on, just to find at the end that everything is okay. Thank you.
Questions from anybody?
Julian Goodwin from Google. Have you seen anything where very low speed interfaces, 1 gig ports on otherwise 100 gig boxes, change anything? Particularly VoQ seems like that would be a nasty case.
The speed of interfaces doesn't change anything. It's just the numbers, right? Of course, if you have high speed ports, right, and for some reason you use it in the on the lower rate, the buffers may be bigger, right? But that's relative. I use the numbers like 100 milliseconds, like just example, right? Everything which is counted in milliseconds is external buffer. It's in the distributed system is like that. So
more since transmission delay would be longer.
Residency time, you mean?
Residency time would end up being longer, and packets.
For the lower speed interfaces, you have the residency time has a couple of components, right? The queuing delay is one of them, and it's a variable one. But the residency time, but if we skip the buffering and queuing, the rest is the deserialization time. Then you have the lookup time. Then you have the let's say propagation inside the node, which takes 9 nanoseconds, but it's there. And then you have the serialization delay, when the parallel data has to be serialized to the output port. But this is all of them are fixed for the given platform. And for the interfaces, it's nature. It's a physical limitation, right? The serialization time is just a function of the packet size and interface speed. So there is no impact on the queuing and the queuing behavior. We are talking on top of it. The only thing from the queuing architecture versus residency time, the only thing is that if you have to send the packet from the switching chip to the external memory, which you have to do if we talk about milliseconds, right? It takes time, because the memory works on some speed. And then you have to read it. Packet may stay in memory or may not. It could be just write and read if the queue is empty. But only that operation takes time. And if you have to do this twice, before Fabric and after Fabric, it's a constant component to residency, to the overall latency. How long the packet stays in the queue, that's a variable part.
Hi, Carl Klatsky, Comcast. So we talked about the latency as you described it. You gave it in the abstract without any impact against the type of traffic that it is. Really, it gets more complicated that when you add in QoS and you say you want to prioritize and minimize latency for a particular traffic type like gaming. When you start doing that, does in this example you showed, the VoQ is basically better on that. Skipping the trade-offs about power and cost, but in terms of just speed through the box for the residency.
Yep.
Does that still hold up when you start bringing in QoS aspects of it?
Okay, I will try answer that way. First, you have the fixed residency time, and it doesn't matter what is your QoS, right? If you need to write the packet to the memory, it takes some microseconds, and regardless if it's a high priority queue or less priority queue. Same with the serialization, doesn't change. The only thing is changing with the QoS that your high priority traffic is taken from memory earlier, so they spend less time in the memory, right? And I, by purpose, do not talk about the QoS. I try to be very specific to the FKF one queue or one set for traffic only, because it's complex enough, right? Sure. So yes, in general terms, the QoS has sense. I didn't say not, but it gives you the latency delta is on top of the residency time, which is given anyway. And this residency time has this component related to the memory read and writes, number of memory reads and writes. And this is one of the difference between VoQ and CIOQ.
Thank you.
I think no more questions.
Yeah. Any more questions? Thank you very much.
Thank you. Please fill the survey. I like to see my performance.